he's talking about leverage domain-specific languages in an interactive score system. Okay, please.
Hello. Hello everyone, so thanks you very much for inviting me. So my presentation will be about an interactive score system. So interactive scores are scores which cover some element of interactivity in the graphical elements or visual elements of the scoring system. So yeah, first introduction, and then we'll consider the place of domain-specific languages, so programming languages tailored for a specific task in this kind of score system, and I do an overview of, well, the software environment. So the software I'm about to present is software which is originally made for controlling external software like MaxMSP, SuperCollider, Pure Data, so only scoring them in time. For instance, tell to Pure Data, play this sound at this point in time, play this other sound at this other point in time, write automation curves. And it works with network communication protocols like OSC, and so I don't know if you know Open Sound Control, but it's very common network messages. And it's a sequencer, so unlike patching software like Max or PD, you basically will have timelines and a temporal axis, x-axis, with interactivity in real timelines. So to control this external software, we first have built a library which is called JSSA and which is integrated in a lot of creative environments. So I mentioned Max, PD, but also Python and quite a bit of programming languages. So here's an example of PD patch with here, so special objects which allow to define parameters in VPatch. So parameters with ranges like minimum, maximum, type of unit. Like for instance, for a color, you can say that it's RGB color and HSV color. So a lot of metadata, and then this metadata is able to be queried over the network. So that is, another software can ask to the Max patch or PD patch, okay, tell me what are your parameters, and they will all get an OSC address automatically. So this is useful then for scoring. So the score will be based about a set of objects that I will present, so visual objects, so for now it's a bit abstract, and processes, which are, well, musical processes that occur in time, so like in some automations, but also MIDI notes, and more generally, any kind of computation. And so the environment looks like this. So here we have all the parameters in external software. So that is, the parameters of the PD patch will appear automatically on the left, and on the central part you draw your score, which harbors interactivity and basic UI widgets to discover what happens in various elements of the score. So, and more specifically, the execution engine is based about the notion of branching timelines, so with interactivity and conditionals. That is, you can say something runs for, let's say, until an event happens, then something else runs, and you can have minimum, maximum times for things to happen, and conditions. So all the interactivity is expressed through the OSC-like messages. That is, you base your expressions and the conditions on OSC-like messages and values like slash volume is greater than 1, and if your OSC parameter is mapped to a volume slider, then you can control your score separation with your interaction. So the main question we had is how to perform relevant musical processes in this score, because for now it was only a temporal specification, but which couldn't do a lot of useful things. So one thing we didn't want to do was to introduce basic computational objects like in Max or PD with plus or list operations or very low level stuff, because it's an environment really tailored for composers. We really don't want generally to learn the intricacies of programming languages. So we wanted to stay on the higher level of programming, and with very broad and very general objects, which could then be implemented more specifically by, well, expert programmers. So the idea for this is to find a relevant set of domain-specific languages which would be tailored for specific programming tasks in the environment. So domain-specific languages are languages which will, let's say, do one thing and do it well. Like, for instance, we'll see quite a bit, but some multiple researchers in the programming language community have shown that domain-specific languages are a very efficient software engineering pattern. That is, it allows to develop software more quickly, and in our case, since the music score is basically a software in itself, we believe that it will increase the efficiency of creating the music score. And so, like I said, the point of research is not to recreate another programming language, but to find which programming language can integrate together in a score system, so for interactive music, so with a lot of constraints, and to create music easily. And so, as I mentioned, OSC and various protocols, you will say that it's already possible, because you can just send messages to Max, and Max will generate sound, and you will be happy. But this has a lot of drawbacks. So the biggest of them all is that it's not sample accurate. That means you can send network messages, but you don't have any timing guarantees on when your message will happen. So you can say, for instance, play a sound at 7 samples and another sound at 9 samples. While if the environment itself has the capacity to call code basically to generate sound, then you can be sample accurate and have precise positioning of sound effects. And besides this, sending network messages has a fairly high cost when relating to just communicating directly in the same process. So we took 5 criterions to find relevant domain-specific languages. So these criterions are first dynamicity. That is, the language must be able to change during the execution, because when you write a score, it's a fairly dynamic operation, and you don't write a fixed score, but the composing process is always dynamic and you always change stuff. Reflectability is important to know from a given program, to know how to map the program's input and output to our score. That is, if for instance I have a program which takes a frequency value and outputs sound, I must have a way to know what will be these inputs and outputs, so stuff like audio channels, and how can I know what will I get from my embedded program. And of course, since it's something for music, it has to cater to low latency requirements. So if we want to do, for instance, new musical instruments, we have to be under 1 or 2 milliseconds of latency. So it mustn't be a language which takes a lot of time to process. And since, due to the characteristics of our execution engine, the programming environment must be able to, for instance, have multiple instances. Some software environments are limited to 1 instance in a single process. We don't want this because it will go against the latency requirements. And finally, something which is relevant for artistic works, so like something that you will use as part of a compositional process, and not programming languages which is only useful for industrial requirements or stuff like this. So we chose, for now, 5 languages. First one is Faust. So Faust is a French originating programming language which is tailored for sound synthesis. So it's a simple, default example which shows how to write a synthesizer in Faust. So as you can see, it's fairly short. It's a functional programming language. And so that's one of the languages we integrated. Another is JavaScript. JavaScript with the QML environment, which is based on the Qt library. So something is a bit weird here if you know programming languages, because JavaScript is not at all a domain-specific language. It's a fairly general programming language, but we restrict it with basically special types which are here to give us what are the inputs and outputs of our program. So it's an embedded domain-specific language in JavaScript. That is, we use special primitives to express specific parts of our system, like our inputs, outputs, and our execution function. So here it's a simple example in the embedded version of the script of another synthesizers. And two others are XPTK, which is a simple embedded environment for mathematical expression computation. So you just give a mathematical expression, you get the result. And fairly often in music research, you have to have some small math equations, and you really don't want to type a whole JavaScript program just to compute the cosine of some function. So it's a simpler way to have very quick expression with less expressivity, of course. And finally, we also try to embed pure data in our environment directly. So pure data is a famous music programming environment. And the advantage of pure data is that a lot of music composers are already knowledgeable of patcher-like environments, so they can just reuse their patch in the program. And finally, for graphics, we've trained currently to introduce a way to generate graphics with a GLSL format, which is, well, basically the language with which you talk to graphic cards generally, and with some added capacities for introspectability. That is, currently graphic shaders aren't introspectable. You can say from a shader what are its inputs, what are its outputs. So some people have devised a way to append some metadata, which use a JSON-like format and which adds basically the types of parameters, means, max, and all the relevant parameters in musical and artistic processes. And here a code of shader. And so I now show the software, if the screen wants to work at least. So so this is the software, which is called OCS Score. And okay, so there are basically it's this timeline, and you just create objects on the timeline. So here it will execute on the x-axis, and currently nothing happens. So it's like I had created empty tracks in Ableton Live or Cubase, except here the tracks have the ability to be branching. So from one track, for instance, you can have two another tracks which will come afterwards, and it will execute. So you can make arbitrary branches, and it's based on, well, a tree-like, or more like a directed acyclic graph of objects. And these objects can have some level of interaction. So here I can say, okay, at this point, wait for an interaction to continue. And here, even though the parent timeline will continue, the child timelines will be waiting, and it's not until I tell them to go forward that they will start. So here I did it by just by mouse, but you can use OSI messages to control the progression of the timeline. Likewise, you can say, okay, after this point, I will only continue if some condition is true. So this part will execute, will not execute, and here, let's go. So as you could see now, I started earlier, and then I just put a false condition. So this part of this score won't execute. But this doesn't produce any sound, and it's not very useful per se. So now I'll show with Max and SP how, for instance, we can communicate. So this is a very small Max, but maybe I'll just make my screen bigger. Okay. Okay, so this is a max patch. So very simply, the one parameter frequency parameter, one square triangle generator, and one parameter for the volume, and one which will receive banks and send them to the software. So from the software, I can just say, okay, let's make a new document. And here on the right part, I can say, okay, add device, and well, the port by default will work. And I can see in this tree what are the parameters of my source. That is, frequency, volume, and I can say, for instance, okay, okay, so here I will just be doing a small automation on my frequency. So here, as you can see, the frequency, so maybe you cannot see, but it goes from 80 to 300 because that's what I put in my patch. So that's part of the introspectability question that I put. So here I say, okay, your range will be from 80 to 300 in hertz, and I can get it in the score so that you don't go out of the bounds you specified in your, well, while writing the max patch. And if I start sound, it's coming out from my computer. Okay, I'm sorry it's coming from here, but if I play, I will just have the max patch, which will increase in time, but the frequency increases in time. And right now that's only with network messages. That is, even if for one message it's fairly fast and we don't notice anything, if you start to have 2,000 or 3,000 parameters, you will start to have latency problems between your different objects. So what we want to do instead is to perform the whole generation directly in the score environment. That is, well, use programs embedded in the score to generate sound and stuff like this. So, for instance, I mentioned pure data. So I made a small pure data patch earlier. So this one with a not input, so conversion from MIDI not to float and oscillator and sound output. And this patch can be loaded as is in the environment. So here, recent files. And here I have a loop in my score, so you can also have looping behaviors, you can have arbitrary hierarchy. So here I can go further and further in, well, not here currently, in hierarchical levels. And I have a PT patch which is loaded here. And this is the PT patch, which is embedded as well, a subprogram in the score environment. And well, the PT patch will only run from this point to this point. So I mentioned, for instance, dynamicity and reflectability earlier. Well, reflectability is what enables us to say that in this patch there is a single not in, there is a single audio output, so the score environment detects it and creates a MIDI input port so that I can send MIDI data to it, and a single audio output port so that I can, well, generate sound. And all the chosen environments behave like this. So for instance, the JavaScript environment will, yep. So here I have a JavaScript script directly embedded in the score. And so with two ports here, one input port, one slider, which will be here, and one output port. And these ports just generate message, and they apply a transformation. So here the transformation is just modulate the input curve with a small random signal. So formula is output equals input plus slider value times random value between 0 and 1. And now if I look at my max patch, connect. And here I set the random to max. I think I just quit max MSP because it doesn't want to go out on the audio output options. Oh yes. Okay. That's better. So here. And my script can be used to, well, modulate a bit in real time, and you can just type some code here, for instance, let's say, okay, 10 times mass random, okay, and now it should be much more random. So you can embed scripts like this directly in your score and compose them in time. So you can apply an effect, for instance, for here for 10 seconds, and then just start doing another script, JavaScript, yep. And like this, we'll just copy it. I can manage it at least. Yep. Oh no, sorry. Okay, we'll copy paste. Doesn't seem like it's working fine. So you can draw cables like this between objects, so it's, well, like patching, but with a temporal dimension. And I hope I'm not too late in time, maybe. Okay. What? I'm sorry? Yeah. How long I still? 10 more minutes. Oh, okay, fine. Okay. So basically, yeah, you have two dimensions to this score. You have the temporal dimension, which goes from left to right, and with objects which execute, well, like this in the timeline, and I would say, the data dimension. So in the backend, there are basically two graphs. One graph to represent the temporal progression, and one graph to represent the data progression. And what happens is that, so if you know data flow environments, at each time slice a different data flow graph is created from the set of activated temporal objects. That is, at this time, only these two objects are in the data flow graph, and at this time, only these two objects are in the data flow graph. And so this basically is a dynamic data flow mechanism, which allows, well, to have scores whose data flow varies in time. So to understand, it's a bit like you could have multiple max patches that were scheduled in a timeline, except the scheduling is done automatically from the activated objects in the environment. So there is so apart from this so pure data and JavaScript scripts, so there are a lot of other embedded languages. So, for instance, I mentioned the expression TK, which is basically simple mass expression. Connect, and here, as you can see, it's just a small formula which doesn't require all the work of JavaScript environment. And if I play this one, okay, here it's more noise-like patterns. And so with this, you can basically have the equivalent of combining small operations in the max patch with plus, cos, and when working with max programs, we had a lot of cases where people were just chaining simple operations, and this chaining of operations has a fairly high computational cost. That is, it's much more efficient to have a single environment which is able to optimize a sequence of computations, than 5 data flow nodes that aren't able to be merged because Max doesn't allow it. So this allows a lot more computational efficiency. And yes, so I think that's mostly it for the environment. And so something else, as I talked about introspectability. So all of this is open source, all of this is in libraries, and all of this can be used in, well, other software fairly easily. So for instance, this part of reflectability of external max patch, well, you can also access them through the network, okay, like this. And if I go here to this address, which is basically the address of this object in my max patch, well, I can just see all the parameters and all the metadata that I added to my parameter. And so this allows very easy communication between creative environments. So you can easily control open frameworks from Max and Max from PD. And basically the idea is to allow composer to work with a cross-environment setting to easily express their scores and to synchronize all these environments in a single one. So, well, to conclude, so right now I've only been working with dynamic and especially interpreted languages. That is, languages where there is a software backend which at each step of the computation looks for what's the current expression and, well, it just it interprets it. And in audio software, it's sometimes not very efficient. That is, you really want to minimize the amount of computational work which is done at each time step to have better performance and to be able to have more behaviors in your score. So the next step for me is to try to find embedded languages which respect the same characteristics as the others, but which are allowed to be compiled sometimes on the fly, sometimes beforehand, but try to find all the techniques to increase performance, basically. And another is to do some usability studies to find first are the languages proposed correct for our use case, that is, well, music composition and more generally new media art composition and creation, and what other kind of languages could we try to embed in order to schedule, well, meaningful art forms. So thank you very much. And so here are the links, so everything is downloadable. And well, if you have any questions, feel free to ask.
Thank you very much. Are there any questions and comments? Shall I confirm something? In your new language, what are the embedded languages? It includes PD, Qt,
yeah.
JavaScript.
Yeah.
What about Max and MVP?
So one of the requirements, of course, is because since all the environment is open source, I can only embed other open source environments, and Max sadly isn't open source.
That's true. So including SuperCollider.
SuperCollider will be interesting, actually. We have so an integration of the network library is already integrated in SuperCollider, and well, I think that could be possible. But SuperCollider is based on itself a client-server architecture. So I think what will be interesting for us to have the same kind of sample accuracy will be to embed the server. So it's not this but well.
Actually, you don't have to doubly define structures, things. One simple question: what's the history of the? How long have you been working on this? What's the first version issued?
Oh, so basically this is based on older research. So maybe you have heard of the iScore software. So iScore was developed at Bordeaux, so at my university, for quite a bit of time. And let's say that there were multiple rewrites of the environment because previous environments were written on Petrinet-based semantics for execution, and I've redone another semantics based on, well, functional.
That's the term that I wanted to refer to. Petrinet is a model which you can dictate using concurrent system. So then data flow.
Yeah.
So I just wondered how close it is.
Well, actually, I disregarded a bit Petrinet. So and I've written a semantic in, well, functional language, and I'm going more towards denotational semantics than operational semantics for it. So because even though there are similarities with Petrinets, we found that some of the specificities, like for instance having conditionals, it starts to add, like, you know, all the extensions to Petrinet, like color Petrinet, time stream Petrinet, and it became unwieldy. So we just took what we wanted from Petrinets and we wrote our own semantics from it.
Well, it's not fair to say Petrinet because not very many people are very familiar with Petrinet. So I just go back to this. So I want to confirm you can express the concurrent system. In other words, you can define the synchronization of what's parts synchronized, and you can define the condition. What happened for each channels,
exactly,
and then what fires go to the forward.
Yes. And so there are basically two kinds of synchronization. There is synchronization at the macroscopic or musical timescape, that is synchronization between two musical objects. So here it's not really musical, but basically you have the guarantee that this starts after this and at the same, so the next audio sample, so that's one kind of synchronization. And you have synchronization at the scale of data. That is, for instance, let's say this. So here, this is a mapping function, which, well, basically linear or you know, all the curved mapping, for instance. And here there is a synchronization at the data level. And so, unlike Max or PD, which are based on an asynchronous message passing method, in SCORE everything is synchronous. That is, all the messages are timestamped and arrive exactly at the audio sample they are scheduled to. So that's a bit different. So two different kinds of synchronization, basically macroscopic and microscopic.
One more question. In Petrinet, you can dictate concurrent system.
Yes.
In other words, many program counters going differently, parallelly.
Yes.
So this, in this demonstration, you can show us the two parallel channels going from the.
Well, they're in parallel, but they're also in sequence. That is, if I could have a pen. Actually, even so, there is visually two concurrent programs. The data for this is script and goes directly in mapping. Well, for this, Petrinets can be useful with passing tokens from here to here, I guess.
But the program counter can be split into multiple dots.
Yes.
That means starting from one process, the multiple processes
indeed
differently run.
Yes. Well,
Can possible. This program language have an ability to express this multiple
you can have
going on.
you can have, I'm just trying to write it quickly, so that's the problem with visual languages, everything is done with mouse. And what do I have here? LFO, for instance, so here I have an LFO process. So I could say, the output of this one also goes to this frequency, so you can send, the tokens can go at the same time, and it's synchronous, so it will be, to create token application.
Okay, thank you. I just explain a bit in Japanese. ペトリネットっていうのがありましてですね、非常に数学的なというか工学的なモデルですけども、それが表現できるって彼も言ったので、ちょっと確認したんですね。で、普通プログラムって1個だけかと思ったら、 並列プロセスっていうのは一度にたくさんこう走れるわけですから、最初1個でスタートしてもどっかが発火して何かあると次から次へといろんなプロセスが同時に走るという並列プログラミングが書けますかという質問で、できますという答えを一生懸命に説明していただきました。And also you can you have already shown in your demonstration that it has a hierarchical structure and you go to the deeper level at the time. 一応確認ですが、階層的構造を持っているので、中にどんどんこうタイムラインがハイパーテキストのようにこう中に入っていけるっていう確認をちょっとしました。
You can go deeper and deeper, and well, nesting is there is no limit of nesting.
Okay.
So, and likewise, it's synchronized.
I changed my turn.
So I'm interested in the data structure between each small programs. So
you mean that if you run?
I mean for example, PD and JavaScript program. How translated the data structure? I mean, I want to implement the original data structure to this system.
Yeah.
So how communicate each program?
Yeah, of course. So here, what we did is this part here, we call it the tree, defines basically a tree of variables, and these variables can have multiple types. So types are float and int and string and some others, and also some MIDI data and audio data. So MIDI is just MIDI bytes, and audio is multiple vectors of samples. So, and to communicate, basically, if you know, for instance, how to make a PD external, it's fairly similar.
So you mean that it's only communicator? It's only scalar values.
Either scalar or vector values. So.
So cannot communicate with the JSON. For example, JSON.
Okay.
Tree structure.
Yeah. So there are two parts. So there is internal. So if you want to embed something directly in the program, yeah, it's C++. So you have to provide C++ plugin. But if you want to do communication like with Max, here is JSON.
Yeah,
and
I understand.
The protocol is called oh, sorry, I don't have internet. But okay, I just write it down. So it's based on OSC, and we added a query system to OSC. That is OSC parts, so UDP, and query part is based on JSON on top of WebSockets. So fairly standard for current year. And with this, you just implement the WebSocket protocol, and you can send and receive message. But it's backwards compatible with OSC, so you can just send OSC messages. So if you don't know, it's messages like hello frequency, and for instance, it's the OSC address, and here a float and an int and a string. And OSC is a fairly simple protocol to implement.
So you mean that we should finally implement it as strings?
It's a binary.
Binary strings.
Yeah, this is string, but this is binary.
With the OSC
yeah,
implementation.
It's one possible way, but actually the environment implements quite a bunch of protocols. So there is OSC query, but also some other OSC, but also HTTP, serial port. So we've used for robot performance, and MIDI WebSockets, and well, audio is a bit particular. It's the audio output of the sound cards, for instance. And we are trying to add all the relevant protocols for artistic performance, because well, that's what software is about.
Okay, thanks so much.
Thank you.
他にどなたかありますか？よろしいですか？ Okay, thank you very much for the presentation. それではこれで、